with arrays and linked list in this session. So without further ado, let's start. And let me make few things clear before and anytime do you have any doubt, you can interrupt me in between. They have a mic access, right? Or we'll take Q&A in the last.
We'll take the Q&A at the last, sir. They can type it in the chat box.
You're not audible.
I'm saying that they can type it in the chat box. As of now, we'll have the Q&A session in the last.
I think there's problem in this. I can't hear you, or all people cannot. You guys can hear her? With arrays and linked device session to speaker. Without further ado, let's start. Let me check. And
so I guess
let me make few things clear before. And anytime you have any doubt, you can interrupt me in between. They have a mic access, right? Or we'll take Q&A in the last.
We'll take the Q&A at the last, sir. They can type it in the chat box.
You're not audible. Speak up, someone.
I'm saying that they can type it in the chat box. As of now, we'll have the Q&A session. Hello, am I audible?
I think there's problem in this. I can't hear you, or mic access. All people cannot.
No, sir. They don't have the mic access as
You guys
of now,
can
but
hear
they
her?
can. We'll enable it at the end of the session. Am I audible, sir?
With arrays and linked device session to speaker. Without further ado, let's start. Let me start with and
So I guess there's something wrong
what
with
are
the
data structures, why they are used, and why we use them. And anytime you have any. So data structures can be defined as a group of data elements or data items which provide an efficient way of storing and organizing data in the computer so that can be used efficiently, right? Because whatever program you write, whatever algorithm you use, it is going to consume or use any kind of data, right? Without any kind of data, there is no use of any program or any algorithm. So each and every program you make, each and every task you do, or program, or the algorithm you use is going to ultimately use some or the other kind of data, and to use that data efficiently, to make that used more and more efficient, we use different techniques and different structures which we call as data structures. And for example, we have arrays, linked lists, stacks, queues, trees, graphs, etc., right? And the second point is data structures are created in the memory during runtime of our program to work upon. You know, some students think that data structure are something which are stored in your hard disk or hard drive, and they'll come into your memory when you start your program. That is definitely not the case. The data file, or the file which through which we are accessing the data, that might be in our storage device, but whatever data structure we are going to study, that is going to be created in the main memory during runtime, right? And then data structures are the main part of many algorithms, as they enable programmers to handle the data in efficient way. That is self-explanatory, and it plays a vital role in enhancing the performance of a software or a program, as the main function of the software is to store and retrieve users' data as fast as possible, right? You don't for example, let us take an example of Google, right? You just search any keyword on Google and you find millions of answers in just half a second, right? So the efficiency and how fast our algorithm is working is really important, because you don't you never wait, nah? If you visit any website and if it's taking more than 4 or 5 seconds, you just think that it's not working, right? So efficiency and solving problems as fast as possible is really important, right? So that was it about introduction, and let's jump on to arrays, right? So array, what is an array? Array is a collection of elements of similar data type which are stored in contiguous memory locations, right? there are two key things to keep here, that is similar data type and contiguous memory location. Similar data type means that the data types can be any primitive data type like integer, float, double, or any other data type, and it also can be user defined data type. Like in C you have studied structures, right? So you can create your own structures and also can create their arrays as well, but the thing is they are going to be stored in contiguous memory locations, right? And the second thing is array is the simplest data structure where each data element can be randomly accessed using its index number. In this one, the key is random access. Now, what is random access? See, in this example, you are seeing an array which is having size 8 and it is storing some elements, right? And the index is starting from 0 till 7. In most of the programming languages, it starts from 0, but I don't think there is an, yeah. So in almost all programming languages, it starts from 0, and you can see the addresses at the top as well. So in a typical compiler, integer stores 4 bytes, right? So here you can see that first element has an address 200, then we have 204, 208, 12, 16, and so on, right? And whenever you try to access an element, right, you say, let's say print a of 4, so it will give you the value 5. Now how it is doing that, how it is accessing that element? So that is how that, now I'll explain it. Whenever you declare an array, that right here the array name is arr of size 8. So what arr is a pointer which is storing the base address of the array. And what is the base address here? Here it is 200, right? So if you are trying to access the ith element of the array, so the formula would be base address plus index into size of, here I have taken integer because it is an integer type, but generally it would be size of whatever data type our array is in, right? So if we are accessing the element at index 4, then what will be the formula? Base address, that is 200, plus index, that is 4, into size of int, that is also 4. So 200 plus 4 into 4, 16. So this will give an address 216, and then we can print the value 5 or do whatever we want with it, right? So that was a basic idea about arrays. Let us move to the next slide. Yeah. So there are many types of arrays. You can have single dimensional, two dimensional, and multi-dimensional arrays. What is single dimensional? The array with one subscript. Subscript means that you can say it is a row or a part of array which is storing elements. So one subscript means it is only having a row, right? It is storing elements contiguously and they are arranged in a row. Now, what is two-dimensional? Two-dimensional array is having two subscripts, rows and columns. For example, this ARR is having 3 rows and 3 columns. So the first square bracket we have is defining how much rows it will have, and the second bracket defines how much column it will have, right? And also with the same convention, we can have multiple dimensional array. For example, you have given an example of 4-dimensional array. So it is having 4 rows, columns, then height, so whatever you can name it. You can do that. It is not, an industry standard. We generally use almost all the times not more than 2-dimensional arrays. So you will not be working with n-dimensional arrays very often. It might be in a particular question that you are asked to do so, but generally you are not. It is very rare that you get a question with n-dimensional arrays and so on, right? So let us move ahead. And yeah, so as we discussed that arrays are stored in contiguous memory locations. So how 2D arrays are stored? There are two formulas of the storing 2D arrays, and that is row major and column major. right? For example, if you see here, there is an array which has 2 rows and 3 columns, right? And I've defined it with general values 1, 2, 3, 4, 5, 6. And in the first model, you see it is stored in the form of row major, that is row wise. So the first row is stored contiguously, and then after that the second row is stored. And you can see the address also here, that first starting from 200, the first row is stored till 208, and from 212 to 220 the second row is stored. So that's how row major mapping works. And similarly, you can also have column major, which will store your elements in the memory uh, column wise, right? So in this case we have 3 columns, and if we store elements through columns, so we can have something like 1 and 4, right? First column will have 1 and 4 together, and then second column will have sorry, I've written something wrong here. Oh, sorry. First column will have 1 and 4 together, and second will have 2 and 5, and similarly third column will have 3 and 6 together. So this is how column major mapping works. So you don't have to care about that how mapping is done. It's just for your understanding that how multi two-dimensional arrays are stored in the memory. It is generally the compiler's thing to do. It is not your job, right? Yeah, so that was it about 2D arrays. And yeah, now we'll discuss operations. So there can be n number of operations like traversing, searching, insertion, deletion, sorting. You can also have many more operations. You can find maximum of array, minimum element of array. You can either sort the array. You can do a lot of things, right? So these are what are major operations which we have to take care of when we are defining an array, when we are using an array, right? So these operations we'll discuss in detail now. Right. So this is traversing and linear search. So how we traverse an array? We can use any type of loop, like for loop or while loop. In for loop, of course the index starts from 0, right? So we declare an counter, which in this case is I, to 0, and will increase it till length -1. Why? Because if the array length is 8 elements, so the counter goes from 0 to 7, right? The last element has an index 7. So we'll increase counter and do whatever instructions we can do in this array, right? And similarly, we can also use while loop. We can declare our counter before the loop, and we can run the loop while our uh, counter comes equal to the length, right? For example, if the length is 8, so the counter reaches 7, then the loop stops. I've missed a point here. I've missed in oh, sorry, I've missed incrementing this counter, but you get the idea, right? We will perform some instructions, and then we will increase the counter in the loop as well. Now this is a general form of linear search that you might have already know, that in linear search you are given a key, and you have to find that if that element of that key is present in the array or not, right? So by using simple for loop, starting from 0th index to the last element, we are checking that our element in that array is equal to the key or not. If it is, then we will return true, or whatever we want to return. If you want to return the index, or we just want a boolean value, that it is true or false, so we can do that also. Kushal is requesting control. Okay, so okay, right. So talking about time complexity, so I want to ask you all that you know a little bit about time complexity or not. So if you know that, I can skip this one, or I have to explain this. Anyone? Or in the chat you can reply. Please interact, guys. No, no.
No.
Okay, so let me explain that first. So time, okay, sorry. So talking about time complexity, what we do is it is a big algorithm, right? So there are many methods through which you can get to know what how efficient your algorithm is, but those methods are not generalized. For example, in some languages you have uh, inbuilt function which will provide you the time at which that statement is executed. So for example, before our linear search algorithm gets executed, we can have a variable before it and we can say, store the time at that time, and after the linear search has ended, we can store the time after the search is ended in another variable, and we can subtract those times and get the idea of how much time our algorithm is taking. Array length is n, right? So what, no matter what the length of our array is, our algorithm will, whatever the time our algorithm will take, will not depend on the size of our array, will not depend on n, right? Okay, yes, yes, okay. So it will not depend on time, on the size of the array or n, which we are taking as the size, right? So in that case, what we can say is our time taken is not dependent on the size of array or on size of anything, and it will take constant time, not constant in the sense that it will take 1 millisecond or 10 millisecond. It depends on system to system, but we can say that it will take a constant amount of time to do that searching, because it has to just check the 0th index and it will return true, because we have decided that our element is at the 0th index itself, right? So in that case, when the time taken doesn't depend on the size of the array or the size of any data structure you may work upon, in that case we say that the time complexity is big O of 1. This O we say as big O, and we say that in the best case it would be big O of 1. So this is the best case of this algorithm. And if you are trying to code some algorithm for any data structure or solving any kind of competitive programming problem, this is the best case you can hope for, right? In just one operation your algorithm is over and you have found the answer. How good is that, right? But that's not what happens all the time, right? There are cases when the element will not be present in your array. So in that case, what you will do, right? So this is the best case, but this doesn't happen all the time. Now let us consider the worst case also. The worst case would be that our key is not present in the array, right? So we traversed through the array, we checked all the elements and we checked the last element and it's still not present in the array. So we say that, okay, we'll return false, right? You agree on that? Please say yes or no in the chat.
Yes.
So in that case, the number of comparisons we are doing is directly proportional to n, right? Because we have to traverse through the whole array. And in that case, we can say that our time taken will be proportional to n. And if we remove the proportionality sign, it may become a linear equation of time. Like if t is proportional to n, we can say t equals to kn plus b or something. So our time equation has now become a linear equation, right? So now we can say that this algorithm in the worst case would be linear in time, right? It will not be over in just one operation. It will take at least n comparisons between after that it will stop. So when our time equations comes to be a linear equation with almost with of course some constants as well, because we are declaring any integer at the start and we are incrementing that also accounts for some operations, but we are ignoring that for now. We are kept keeping that in a constant like a n plus b. So we can ignore those constants and we can say in the worst case our complexity will be O of n, right? So that was all about time complexity. Is that clear to everyone?
Guys, you can type it in the chat box.
Yeah, please guys. I can't know that how it's clear or not.
Yes, sir, it's clear.
Okay. Okay. So yeah. So the worst case was that the key is not present in our array. So we'll have a complexity of big O of n, right? So this was all about traversing and linear search. Now let us move to binary search. So binary search is a little bit advanced searching technique. In what the and in that what we do is, let us see the points first. The binary search algorithm can be used only with the sorted list of elements, right? If the array is sorted, then only we can apply binary search. We'll see why it is the case. The binary search first divides the array into two smaller subarrays and then operate on those subarrays. We'll see how that works. So in this, we are dividing arrays into two halves and we are operating on those. And binary search basically reduces the search space to half at each step. That's the same point as above. So let us see how that works visually, right? So in this case, what you have is an array, a sorted array, which is having 8 elements, right? And you can see these are all odd elements, right? 1 3 5 7 9 11 13 15, and you want to search an element 14, right? So what we will do in this case is we will keep 3 counters. The first counter will be low, high and mid. So these will be 3 counters, and at the starting the counter low will be our 0th index and the counter last will be the last index of our array, right? And the mid would be the average of these two counters, low and high. So low and high here is 7 and 0. 7 plus 0 by 2 is actually 3.5, but we will take the floor value and the index would be 3. So in the starting, our mid is index 3, our high is 7, and our low is 0. And we are trying to do something. Let us see how. Okay, I forgot to mention one thing. What we will do is, whenever we find this mid, we compare our element with the mid or our key with the mid. Our key here is 14 and we compare it with 7, like if our key is greater than or equal to or less than 7. So here our key is definitely greater than 7, right? And so now what we can do is we can leave the left subarray. Left subarray is from index 0 to 2. Why? Because the array is in sorted order and we can see, we can logically think, we can see that if our element is greater than the mid, then the element would be definitely present on the right subarray, right? It will not be present on the left one because we have compared our mid with it. So in this case, our element 14 is greater than 7. So what we will do is we will leave the half array and we will check again in the left subarray, which is starting from 4th index to 7th index. So in next, what we will do is we will keep our low to mid plus 1, because we have compared the third index and that half subarray is over. We don't want to search in it because it is definitely not present in that. So our low will be mid plus 1, and still the high would be here because we have still left with this subarray, right? And we again calculate mid, and in this case 4 plus 7, 11 by 2, it will be 5, right? So our mid would become 5. Now we again compare it with mid. Just a second, guys. Sorry. Yeah, so we would again compare it with mid, and our element was 14, right? So 14 will again compare with 11, and we'll see that, yeah, still our key element, which is 14, is greater than 11. So again we'll repeat the same step. We will leave the left subarray and we will keep our low to mid plus 1, that is the sixth index, right? Now again we will calculate mid. 6 plus 7, 13 by 2, that is still 6. So now we have only two elements, and our mid is 13. Then again follow the same procedure, again compare it with 13. Now again our key is greater than 13, so now our low will be again it will be sorry, again it will be mid plus 1. So mid is equal to low, so we'll uh, save mid as seventh index. So now what has happened is we are left with only one element. Only one element is left with us, and if we calculate its mid, it's going to be it is going to the same element, right? So we have high left, high low, and mid pointers on the same index. Now this would be our last comparison. Why? Because we have uh, compared with all the elements and we are just left with one element. If our element is found, then we are good to go, and if it is not found, then we will return false, or will print something that, oops, the array is not found in this array. Oh sorry, the element is not found in the array. So we'll compare it with again, and still it is not equal because our key was 14 and here it is 15. So it is right now it's also not equal, so it will just return false, right? So that's the basic idea of binary search. Please in the chat box at least say yes or no if you understood that. Okay, I can see most yes. Okay, it will be more clear after we see the algorithm. So let us see the algorithm now. So this is an iterative version. You can also use a recursive version of this algorithm. But right now for easiness, we are using iterative version. So as we discussed, we have to keep three variables: low, mid, and high, right? So in our function, what we are having is an array, its length, and the value that we want to search. So at the starting, our low is 0 and our high is length minus 1. So till when we want to loop through the array, till when we want to continue looping is when our loop is less than equals to high. Why? Because loop is the lower I can say lower index, and high is the higher index. And if the element is, if we have left with just one element, then they will become equal. After that we don't need to continue, right? So this will be the condition of our loop, and we'll first find the mid value, right? It will be high plus low by 2, and we'll compare. If the element at mid index is equal to the value, then we have searched and the element is present. And if it is not, if mid is greater than value, if the element at mid index is greater than value, then what we want to do, the high would be mid minus 1, right? Because now our mid element is greater and we want to search in the left subarray. So in this case, the high would be mid minus 1, or else we can increase our low counter and say low equals to mid plus 1, right? So we will loop through this again and again till we have found it, and if loop is over and we haven't found it, so we'll return -1 or whatever we want to return. We want to print and something, we will print that, right? So that was an algorithm of binary search. Now let us discuss the time complexity, and this time it is log of n. It is log of base 2 to the power, it is log of base 2 to the n, but I've written is log n by mistake. Now why it is log n? Let us see that. So in this example, what we had was, we had 8 elements, right? And how many comparisons did we perform? There was one comparison here with 7, second one was 11, and third one was with 13, and the last one was 15. So in 8 elements we performed 4 comparisons, right? And if the element would have been, for example, 16, like if the elements would have been 16, then how many comparison would have been? The mid would be somewhere, let us say our element is still not present in the array, and we have 16 elements, right? So after first comparison, our array would be of size 8, right? We are dividing array into half and half, right? So after first comparison, our array becomes of size 8, that is one comparison. Then after second comparison, our array becomes of size 4, that is second comparison. After third comparison, it is of size 2, and after fourth comparison, it is of size 1. And after it is of size 1, we will do one more comparison, and that would be the end of our algorithm. So in the case of 8 elements, we did was, how many comparisons there were there? There were 4 comparisons. And in the case of 16 elements, there were 5 comparisons, right? So there is a pattern here, right? There is a pattern that we can say that in the case of 16, our comparisons are log to the base 2 of 16 plus 1. Like log to the base 2 of 16 is 4, and we did one more comparison. So it is log to the base 2 plus 1. So earlier we discussed that if our time equation has some constants, we can ignore them. So doing that in this case also, we came up with the complexity of O of log n, right? Is that clear to all of you? Please say yes or no, whatever you think. Yes, yes. Please interact, guys. We need more people to say, okay, best case and worst case here. Okay, we will cover that. Yes, yes, yes. So I think all of you are understood. Okay, so the best case here is so the best case would be our low is 0 and our high is length -1. In the case, let us explain through here, right? So here low is 0 and high is 7, and our mid is index 3. So if we are searching element 7, then in only one comparison we found the element, right? So in the best case, it would be O of 1, because we did only one comparison, and worst case would be the element is not present. That's what we discussed, right? So the best case would be O of 1 and the worst case would be log of n, right? Okay, so let us move further. Okay, now we are discussing operations on the array. So first thing is we are inserting into an array, right? So let us not see the code first, let us see the visual representation. So in this example, we have 5 elements in our array and it is filled with 4 elements with from starting from index 0 to 3, right? 1, 4, 5, 8, and a new element 10 has to be inserted at second index, right? At the place where 5 is placed right now. So what can we do here? The only solution to this is we have to shift all the elements to the right, to one place to the right after this, starting from this index itself, and we have to make a space for our element to get inserted. So what we'll have to do, we'll have to shift the elements from let's say this third index to 4, and then from second index to third, and then we will have a space to properly insert our 10 into the array, right? So that's what we did here, that we shifted the elements by one place. 8 is shifted from third index to 4 and 5 is shifted from second to third index. Now still the second index stores 5 and we can set that element at that index to 10. So that is the idea of insertion. And let us discuss the best and worst case here itself. So the best case would be the element at, we want to insert any element at the index 4, right? So there are no elements in at that index right now. So we'll just have one operation. We will set the value at that index to whatever value we want to insert, and that would be that's it. We have inserted our element. And what would be the worst case in that? Let's say we want to insert 10, the same element, at the 0th index itself. So in that case, what is happening is we have to shift all the elements to the right side, right? Because we have to create the space for that element. So we have to shift all the elements in that array, and then we will be able to insert at 0th index. Yeah, this is a bit costlier process. So that is the best case and the worst case. So let us see the algorithm for that. So this is an insert function. We have an array, we have a length given and the value, and of course the position at which we want to insert. So what we are doing is we are starting a loop from the end to our position, right? From the end to our position, that is the second index. So we are starting the loop from end to our position and we are assigning the value at index I to I plus 1, right? That's what we are doing here. We are shifting. So starting from 4, we assigned the value 8 from index 3 to index 4. So index 3 and index 4 will have 8 values. Then we decreased our counter. Then we assigned the value at index 2, which is 5, to the index 3. So we have 5 at index 3 and we have 8 at index 4. And we have shifted both the elements one index, and then we can insert. So that's what we are doing for I equals to length minus 1 to our position. We are shifting the elements, that is we are assigning a of I plus 1 to ai. And after this loop ends, we can just assign the value which we want to insert at that position. And yes, and also we can increment our length because length has increased, right? And there is one case in here that if this array is of size 5 and all the elements are already present in here, then we can't insert it. then we can't insert an extra element. Why? Because array size are fixed, and it has to be decided at the compile time only. Like you all have studied C, right? So in C you can't do something like you take an integer as an input and you uh, create an array of that size. That is not applicable in C. However, it is applicable in C++ in Java, but that's not what you can do in C. So the size of array, whatever you are creating, has to be explicitly mentioned in beforehand, right? So that's what happens in the array. And in same in the best the time complexity for this would be, in the best case of one, the best case would be we are inserting at the last index, and the worst case would be O of n. Why? Because we have to iterate through the whole array once and we have to shift all the elements, and we will insert that element at the 0th index, right? So this was all about insertion. Any questions or any doubts, or you didn't understood, you can say that in the chat. Screen is freezed. Is the screen freezed? I'm changing the slides.
No, sir. It's visible.
Okay, so let's move forward then. Okay, so that's how you insert, and now we'll see deletion from an array. So first we'll go to this. Now we have the same example as previously shown, and we want to remove that element that we inserted in our last example. In that case, what we have to do, we have to do the opposite of what we did in insertion, and we have to shift all the elements to the left side. So that's what we are doing here. From the last index, we are shifting the elements, and yeah, and that after that our last index is free, and we can do whatever we want with it. We can either set it to 0 or whatever value. So let us see the algorithm for that. Yeah, so delete is a function which is taking array length and the position at which from which we want to delete an element. So we'll loop through the array and shift the elements from I plus 1th index to ith index. For that, we are using for loop here. For I equals to position to length minus 1. In case of insertion, what we did was we started from the very end and we came to our index. Now we want to do the opposite. So we have to start from the position itself to the end of the array, and we are shifting the elements, that is we are setting a of I to a of I plus, oh sorry, we are setting the element at a of I plus 1 to a of I, and after that loop is over, we can decrease our length, and yeah, that's it. We have our insertion. Now the best case, what would be the best case if we want to delete an element from the end itself? So you have to just decrease the array length, and that would be over. And the worst case would be that you want to delete from the 0th index. So you have to shift all the remaining elements from ith position to I minus 1th position. So that would be your worst case. So in both the cases, in best case, we have just to do one operation, and the worst case, we have to iterate through the array once. So that's why we are having a complexity of O of n, right? Yeah, so that is it of deletion. I hope that is clear to you all. Please, guys, at least write it in the chat box if it is clear or not. Okay, we are seeing, yes. Okay, so let us move forward then. Now we are now we'll see a sorting algorithm, and that algorithm is called bubble sort. Now what that algorithm is this algorithm works by repeatedly swapping the adjacent elements if they are in wrong order. Now what do I mean by that? Let us see an example here. We have an array of size 5 and these are the elements, right? 5, 1, 4, 2, 8. These are the elements. Now what we are doing is we have to do multiple iterations through the array and simultaneously check that if the element are in wrong order or not. If they are in wrong order, then we will swap them. Now what do I mean by wrong order? By wrong order, I mean that the element with higher value is having the lower index, right? What is sorted array? The array with the element with the higher index is having a higher value, right? So let us see this through a visual representation. In the first iteration, what we have is by these green colors, I have shown that which two elements are we checking. So we are checking 0 and 1 element at 0th and first index, right? So starting from 0 index itself, we have 5 and 1. So they are in wrong order. So we have swapped them. Then we have increased the counter. Then we have 5 and 4. So these are also in wrong order. So we have also swapped them. Then again we'll check. We'll go for 5 and 2. And these these are also in wrong order. So we will again swap them. And at last we'll check 5 and 8. And these are in correct order. So we don't have to swap them. So this was the end of our first iteration, right? And after we have iterated through the array once, what has happened is the maximum element of that array, which in case it is 8, is at the last, right? Why has that happened? It has not happened in this case because the highest element was already in place in the last spot. But if I would have kept it in the starting, still it would have ended in the last position. Why? Because we were iterating and we are comparing all the elements. We have compared all the elements one by one, right? So the maximum element is definitely going to get placed at the last, right? After first insertion, after first iteration. Is that clear? Why the last, the highest element is present the last place? Yes, okay. So similarly, we will do second iterations. We'll check again. We'll check. So by the yellow block, I have declared that this is now 8, which is, and this is placed at its correct position. Now we don't have to check this 8, the last element. We can iterate till the second last element now. So our iteration length has become smaller. So now in the second iteration, we are checking again 1 and 4. So they are in same order. We are doing no swapping. Then 4 and 2. So they are in wrong order. So we are swapping them. Then 4 and 5. So they are in correct order. So we don't need to swap them. So after this second iteration, we can say that the second last element is also at its place. But we can also see here that our array is already sorted, right? 1, 2, 4, 5, 8, it's already sorted. But the algorithm doesn't knows it. The algorithm still doesn't knows that it is already sorted. It is a problem with this bubble sort, and we will try to solve it in our optimization. So yeah, if it is still sorted, but still our iteration will take place on 3 elements, right? After this third iteration, our fourth our element, our third last element is at its final position. Then at the last iteration, we will just check the first two elements, and we are good to go. Our array is whole sorted. So let us see the algorithm for it. Right. So in this algorithm, we are having an array and we are given the length of array. Right. So first we are having two variables which will be the indices of the elements in the array, and we are using two for loops. Right. So the first for loop is starting from 0 till n minus 2. The I will reach till n minus 2 and will perform. So the outer for loop will perform n minus 1 iterations, right? Because it's starting from 0 and till n minus 1. Why? Because here we saw that our size of array was 5 and we did 4 iterations, right? So definitely we have to do at least n minus 1 iterations to get our array fully sorted. So that's our outer loop. And in the inner loop, what we are doing is we are iterating again, and we are checking that if ARR at j is greater than ARR of at j plus 1. If it is true, then we'll swap them, and if it is not true, we'll not swap them. We will just continue. So that's your bubble sort algorithm. And now in this case, it is a little bit, I would say, not it will be same for the best case and worst case. Why? Because let's see the best case. The best case would be that our array is already in sorted form, right? But this algorithm doesn't know it, that it is in sorted form. It will still perform those operations. It will still perform nested loops, and still, so here still it will perform nested loops. So in that case, we have the complexity of O of n square, which is higher than O of n, which we saw in insertion and deletion. Why it is O of n square? Because for each iteration we are looping through the array. So let us say that we are doing n minus 1 iteration, and for all that iteration we are again iterating in that nested form. We are again iterating through the array. So definitely our operations are not proportional to n. They are proportional to n square, right? So in the best case it will be n square, and in the worst case also it would be n square. Why? Because the in the worst cases, the array is sorted in the reverse order. That is, the highest element is at the start, and we have just transposed the array, or we have flipped the array, right? So in that case also it will be O of n square. But it is right now it's very slow, right? O of n square, that is n square operations proportional to n square in the best case and also in worst case. So that is little bit slow, right? So what if we can check after every iteration that if the array is sorted? Like for example, we did first iteration, and our first iteration result is 14258. And in this case, if we can perform a check that if the array is sorted, then our work is done. We can break through the array. We can break through the loop, right? So in this case, our array was sorted after second iteration, but we couldn't stop the algorithm after right there. We had to do all these iterations as well. So how we can stop that iteration there itself? So for that, I have applied a little bit optimization in our algorithm. We are doing the same thing, but with one extra variable, that is a Boolean variable with name swapped. Now in each iteration, what we are doing is we are keeping that swapped boolean value to false, right? So by default, in each iteration it is false, and if in that iteration we swapped any of the elements, right? If any one element or all the elements were in wrong order, our swapped would become true. So it's like a check. So after we have iterated through the inner array, we'll check that if swapped is false, that is, if the array was in sorted order or not. If it would have been in sorted order, the swapped boolean variable would still be false, right? Because we didn't enter the if condition and we skipped the if condition in all the cases. And if the boolean, if the swapped is equal to false, then we will just break through the array, right? So in this case, let's say we have a sorted array, right? We have sorted array which is something like uh, this one. We have 1 2 4 5 8, and we are starting our first iteration. So we have checked all the elements and we didn't swap anyone, right? So in that case, the if condition will be applied and we will break through the loop, will break the loop, and in that case our complexity will be O of n. Why it would be O of n? Because if the array is sorted, we just iterated through the array once and our work was done, right? And in the worst case, it still would be O of n square, because we have to do n minus 1 iterations and we have to check all the things, internal details as well. So is this clear to everyone? Please say yes or no. Okay, Satyam says yes. Only, okay. There are many yes. So I cannot see any no here, so I'll continue. Next thing is a problem. It's a very interesting problem. Let us try to solve this one. Just a minute, guys. Okay. So the problem is that given an array of integers of size n, find the maximum sum of k consecutive elements in the array, right? So you are given the size of the array and also the array, obviously, and you are given k that is smaller than the size of the array. That's definitely the case. And you have to find the maximum sum of k consecutive elements. Like for example, in this one, the given example, the array is 100, 200, 300, and 400, right? And the k is given 2. So let us see the first, let us check that which elements will give us the highest sum. So the element at 0th index, that's 100 and 200 will give 300, 300 and 200 will give 500, and 300 and 400 will give 700. So that is our maximum sum in this case, right? So what would be its uh, idea, how to solve it? So our initial um, our initial way would be brute force. Brute force is we are trying each and every combination and we are searching for the maximum value. So we have an function array of max sum, and we are having array and nk. These three values are passed to us. So first we will declare a maximum sum variable, and we will initialize it to minimum value of what an integer can afford. that is minus something 2 million or something. This is a general idea what I've given to you, that integer dot mean value is the most smallest value a integer can have, right? Then we are iterating through the array from 0 to I equals to n minus k plus 1. Why we are doing this? Because let us this one. So this was an array of 5 of size 5 and k was given 2. Let us say k was given 2. So in that case what we have to iterate it through, that let us say k is 2, so we'll have 5 and 1, then we'll have 1 and 4, then we'll have 4 and 2, and we'll have 2 and 8. So we have to stop and we compare, we will add 2 and 8. So for that we are uh, keeping the max value of our counter to be n minus k plus 1, and we'll have another uh, let's say another variable current sum, which will help us provide the sum of that k consecutive elements. So for k j equals to 0 to k, we are uh, calculating the sum, right? Calculating the sum of first k elements. Then we are checking. Then after the inner loop is over, then we are checking that if our sum bit which we got from our current sum, it is greater than our maximum sum or not. If it is not, then our maximum sum would be the same, and if it is greater, then our max sum would be updated. So we are doing this again and again. We are iterating through the array. We are checking all the consecutive k elements, and we are finding the max sum. And at the end, when these two loops are over, we will return max sum. So this is the basic idea, the first initial idea of what I am trying to explain. Right? Is this clear or not? Please answer. Got it. Okay. Only Aditya got it. Okay, it's clear. Okay. But sir, it is not sorted. So that is, we are not considering if the array is sorted or not. We are only checking if of the we are checking only the sum. We are not considered about if it is sorted or not. Okay. Okay, so let's continue. Now let us see what will be the time complexity of this one. So we are iterating through the array. That is our outer for loop, and in that loop we are again iterating from we are iterating k times in our inner loop, and we are all iterating n minus 1 times in our outer loop, n minus k times actually in our outer loop. So that equation would be, the time equation would be n minus k multiplied by k. So it would be somewhat of n into k of plus some constants, right? So in this case, what it has happened is we have two variables. We have and also we have k also. So we have to consider them both, and we can say that a time complexity is O of n into k, right? So that was the initial approach. Now let us see the little bit optimized approach for this one. So this technique is called window sliding technique, and in this what we are doing is, let's say we have this array, right? 5, 2, minus 1, 0 and 3, that has size n equals to 5, and k, that is the subarray that sum we want, of that sum we want is 3, right? So the first subarray would be 5, 2 and minus 1, right? So what we are doing is we are calculating this sum of first subarray at the starting, and we are keeping it safe with us. So this was the first thing we did. Now for the second subarray, what we have to do is a second subarray would be starting from 2 and it will be till 0, right? So what is actually happening in this one is we are deleting 5 or we are subtracting 5 and we are adding 0, right? So we can do something like we can iterate through the array with our sum of these subarrays. We can just iterate through the array once and we can after each our counter is increased and we can subtract our this element which is not going to be present in the next subarray, and we will increase the we will add the element which is going to get into our window type thing in our subarray, right? So this is like a window. This whole array is like a big window, and this small section of 3 elements is like a glass, and we are sliding this glass through the array. And what is happening is our when we slide it one index ahead, our 5 is getting removed and our 0 is added to the array, right? So that is how we can optimize this thing. So what we can do is we can calculate the sum of second subarray by adding element at index 3 and subtracting element at index 0. So that will help us to find the sum of next subarray in minimum amount of time, right? We won't be iterating through the loop inside a loop. We will just do two operations, that is subtracting and one subtraction and one addition. So this is the optimized approach, right? So in the maxsum we have an array and we have the size and we have k, same as the last one, right? So first we will compute the sum of first subarray, right? We have maxsum equals to 0, and for I equals to 0 to k minus 1, that is first subarray, we are adding all the elements, right? Maxsum plus equals to ARR of I, which is the same as maxsum equals to maxsum plus ARR of I. So we have calculated the sum of first window, that is the starting window. Now computing the sum of remaining windows by removing first element of previous window and adding the last element of current window, right? So window sum we first declared it with maxsum, and we will loop. Now in this case we have to iterate through the loop only once, okay, right? So in this case what we have to do is for I equals to k, right? First subarray was till k minus 1, and from where we have to start, we have to start from k. For from k to n minus 1, that is the end of our array, what we'll do is in the window sum we will add the element which is going to be included in our next window, which is in this case 0, and we are removing the element at I minus k, right? Which is going to get removed, and we are comparing with the maximum, that if it is greater than the maximum, then the maximum would become that, and if it is not, the maximum would be the same which is already calculated, and we'll return the maximum, right? So this is what we are trying to do in the optimized approach. Any questions or any difficulties? Okay, could you explain this once again? Okay, let me explain this once again. It is a little bit hard to understand. So what we are doing here is this sum of three elements is our first window, and when we are going to calculate our next window, the one element at the index 3 will be added and one element will be removed. That is what is happening, right? There is nothing new happening. 2 and minus 1 will be the same, and only one element will be inserted into the sum and one element will be removed. So that is what we are doing here. That is what we are doing in this uh, uh, instruction, that is window sum is equals to window sum plus ARR of I minus ARR of I minus K. Yeah, so that's it. Okay, so let us discuss about the time complexity. So first uh, we iterated through the array to get the sum of the uh, first window, right? So that is a loop, and there is another loop, right? So we can say that our time complexity would be of n plus k, right? Because there are two loops, but still what our k is definitely either equal to n or less than n, right? And we still have our time equation which is linear in nature. So in this case we can ignore the k and we can say the time complexity is O of n. Any doubt in this one? Or you can say yes or no at least. What about 0 to k? So we included that, right? We calculated it beforehand, right? In the first for loop. Okay, so I'm going to continue. I'll have the question answer in the last. Okay, so now we have our next data structure, which is linked list. Now, what was happening in the array was we were storing our data items or the uh, elements in a particular block of memory that was contiguous, that was one next to each other, right? But there can be another way as well of storing a list of elements. There can be another way as well, and what that way can be is we are storing the elements randomly in the memory. There is no rule such as we have to store them one next to each other. We can store them anywhere in the memory. So this is what is the basic idea of linked lists. So a linked list is a linear data structure, of course, because uh, it is in the form of a linear structure, and in which the elements are stored at random locations in the memory. There is no restriction in storing the elements. We can store uh, elements anywhere we want, not anywhere we want, that anywhere our compiler sees the memory is free, it will allocate memory for that element in that place, right? So from now there are some naming conventions which you have to take care of. The first is that each data item in our linked list is called node. We will see why it is called node, and it will have two parts. The first part will contain the information, that is the element or the data part, and the second part will be the address of the next node in the list, which is also called the link part. Now, why we want to store the address as well? Why we are creating a big block which is having two parts? We could have just gone in just in one block only. Like we would have a insert. We would have stored just the element part of those as well. But the problem in linked list is, as we are storing elements at random locations, there is not a particular formula that we will be able to apply, and we will be able to access all the elements through it, because it is the storage is random, right? So you can't declare a formula that this will be the formula and you can access it directly, all the elements directly through it. That's not going to happen. So in that case, we add another thing to our node, which is a data member of this linked list, which is the address part. So what is happening is, in this example, is this linked list has three members or three nodes, right? The first node has a data 30 and the and a link part, right? We will discuss it in more detail. The second has the data 20 and the third has data 10. Now the address of first node is 505 and the address of second node is 800. So this next part is doing in the first node is storing the address of the next node, and similarly the second node is storing the address of third node. But the next part is a pointer, right? It is pointing to something, right? It is storing the address. A pointer is just storing the address of some variable. So now the last element, because it is not storing the address of something and this is the end of our list, will just make our last pointer to be null. So this is what a linked list looks like logically. And this is another naming convention which you are seeing, that is head. And what that head does is uh, it is kind of an industry standard, right? So uh, when you will try to solve some questions on online websites or in your written rounds of your interview, what you would be given is this head. So this is what this head does is, this points to the first node of our linked list. This points to the first node of our linked list. And what if, then what, how we will traverse through the list, how we will make this head go to the end, we will see in the next slides. Again, there will be some operations, same as in the array, that is creating, this is the new one, that is creating a linked list, traversing, insertion, deletion, and searching, right? So now creating a linked list. So I've included two methods, right? The first one is through a class and the second one is through a structure. Uh, some of you who don't know C++ or Java, you can create a structure in C, and what the structure is holding, the structure name is node. That is same node as we saw here, that are three nodes present here. And that what the structure is holding is a data part and a pointer to node itself. That is, it can point or it can store the address of some node which is randomly stored in the memory, right? That's how we will connect, that's how we'll make those links, right? That's how we will connect these nodes together. So the next part, so this is a pointer of type node. So why we have included pointer of type node, because whichever type the node is, whichever type is of our pointer. So you have studied at least C, right? So you know what pointer is. And a pointer is basically what it's doing is, it is storing the address of some variable, and it is a rule that whichever variable it is pointing to or whichever variable's address it is storing, it has to be of that same type. Like a pointer of integer type will store the address of integer variable, a pointer of character type will store the address of character variable. Now in this case we are creating our own data type which is called node, so we have to create a pointer of that type in this one, and we'll name it, we have named it as next, because through this we will traverse through the list, and this will store the address of the next node. Similarly, you can create a class also, but we will not focus on this one because most of you don't know Java, right? So now comes the traversing part. Let us define traversing here. Traversing is the process of accessing each node of the list exactly once to perform any kind of operation, right? That's what we did in arrays. We kept a counter and we uh, incremented that counter, and that's how we traverse through the array. So that's the same what we are trying to do here as well. Okay, so how the algorithm works is, let us name the function as traverse, and we are given the head, right? So in all the questions which we'll do of linked list, you will always be given the head node or any kind of node in the list, head pointer, right? So we will declare a temporary pointer which is p, and which will store the value of head. And while p is not equals to null, what we will do is p equals to p is next, right? P equals to p is next. Now what this p equals to p is next means, that right now head was storing 505, which was the address of first node. Now if I make the head equal to the heads next, what is heads next? Heads next is 800. So if the head is equated to 800, that is head is storing 800, then head will point to the next node. So now after doing head equals to head next or p is equals to p is next, what we have done is we have we have uh, we took this pointer to the next node in the list. This is what p is equals to p next, or head equals to head next does. And in that we can process the data part of our node, whatever we want to do with it, right? And we can, and in the last we can just return. So of course we are iterating through the list, or we are traversing through the list. So the time complexity will be O of n, where n is the length of the list. Any doubts or any doubts will be covered later. If you understood this, please say yes or no. Okay, there are no pointers in Java, so how linked list is used there? Okay, we will cover that in the last. Yes, yes. If language doesn't support pointer, then how? Okay, we will cover this in the last. We will definitely cover this. Let's move forward. So all the questions would be answered in the last. No worries. But right now, just focus on understanding the concepts, right? So now the next thing is we are inserting the node into a linked list as we inserted into an array. So in this, there can be three cases: inserting at the beginning itself, inserting at a given position, or inserting at the end. So these can be three cases. To explain it more deeply, I have divided into three cases, in the insertion into three cases, to make it more clear for you guys. So insertion at the beginning. Let us see through the diagram first. Let us say this is our array, right? The head is pointing towards our first node, and first node is pointing towards next. The second node, which is having value 20, and this is pointing nowhere, it's null. Now the first thing we want to do is, definitely if we are inserting, we want to create a node, right? It is not the same as array, that array is predefined and all the elements are not present and we are inserting. This linked list, what it is doing is, it is storing the memory as much as it requires. That's why we call it dynamic, because we can increase or decrease its size dynamically while we are running our program, right? So what we are doing here is, firstly we are creating a new node. We are storing whatever value is given to us to insert into that data part of that node, and we are making that link to our first node. And how we are doing that? We are equating that node's next pointer to our head. Let's say head is storing the address of first node, And if we equate head to our next part of the newly created node, it will be pointing towards the first node, right? And then after that, what we can do is we can point our head to the newly created node. So we have, what we did in insertion was we created a new node and we changed the links in such a way that our new node is created and the head is pointing towards the newly created node, and its next part is pointing towards the node where which was the first at the very beginning. Let us see the algorithm. Just a minute. Right. So I made this function as push, and it is having a value which has to be inserted. Now, now the first thing we have to do is we have to create a new node. That is, we have to declare, we have to initialize our node. We have to declare its memory somewhere in our program. So we have created a new node here, and we have set its data part to the value which is passed to us. Now, let's say in case our head is null. When will our head will be null? If there is no node in the list, if the list is completely empty, then what will happen is we will point our head to the newly created node, just as we did in this case, which is the third diagram, the last diagram. So if it is pointing towards null, we'll point it towards our newly created node, and its next part would be null. So this head is pointing towards value, and we have created a new node, and the t's next would be nulls. And if it is not the case, then t's next is equals to heads. That means the newly created node which is storing the value, its next would be head. That is, it would be pointing to the first node, and then what we'll do is we will equate head with the t. We will put the address of t, which is the newly created node, to our head. So this operation, what will do? It will point our heads towards the newly created node. So that's how insertion takes place in linked list. Okay, it's clear. Explaining link in slide. Okay. So let us move ahead, and now we are inserting at the end. Now what we have to do if you want to insert at the end is, first we have to traverse till the last node, right? So that we can have the access to our last node in the list. Then we'll apply the same procedure. We'll create a new node, we'll set its value to the value which is provided, and we will set the next part of our last node, which was pointing to null, to our newly created node, and its next part would be null. So that is what we are going to do if we are inserting at the end. Now first, again we have created a new node here in the first step. Then we have set its data to the value we are given, and we will iterate through the array. Now we are using a while loop here, and we are saying that while head's next or its next part is not equals to null, then you can iterate, and when it becomes null, we can stop. Why is that so? Because if we reach the last node, then definitely its next part would be null, and then we can stop there. Then we can follow our procedure which of inserting the node. So after that, what we will do is our head which is pointing to the last node, its next would be pointing to the newly created node, which is this one, which is storing the value, which is t, and we will put t is next to null, right? And here the same, we are iterating through the list, we are traversing, and since we are doing so, the complexity would be O of n, right? And if we want to insert at a given position, the steps would be the same. We will have to traverse first, so we'll see how we'll traverse. This is a temporary variable. Let's say we want to insert at the second index, so we will traverse till the first index, create a new node, point it towards second index, and we will change the link as shown in the diagram. How we are doing that is, let us see. So first of all, we are storing head in a temporary variable because we don't want to change the head, because head is pointing at the start of the list. Then we created a new node and we set its data part to the value which is given, and we will iterate through the list till we reach the uh, previous node of where we want to insert. Let's say here we want to insert at second, so we have to at least go till the first node, right? Why? Because first node is storing the address of second one, right? So at least we want to access the first node so that we can change the links and we can insert a node in between. So what we'll do is, we have reached the first node and we will point our next part of the newly created node to the next of where we have reached, right? So you can see that uh, temp reached at the first index, and we created a new node and pointed it towards the last node, or the node of the next node of that list. And the next what we did was, we created uh, we pointed temps next to t, right? Temp is the previous node of which we want to insert the value, and we will point its next to the newly created node. So that's how it's going to work. Similarly, we will have to delete, see how we can delete the node from a list, right? Delete. So in this case, we'll have two cases. We'll delete the first node, or we will delete at a given position. So if we want to delete the first node, right? So if our head is pointing to the first node and we want to delete, it's very easy, right? We can just point our head to the next one, and we can delete or deallocate our first node through the memory. So we will just do one operation. We will point our head from first node to the second one, and we'll delete our first node, and that's how we are done. So what would the algorithm be? In delete, what we are doing is, first we are checking that if the list is empty or not. If it is empty, then we can't delete because there is no node present in the list. So what we are doing is, we are checking if this node is empty or not. And what is empty function is doing, that it is checking that if head is null, then return true, or it is returning false. So if we are checking if it is not empty, then we will point head towards the next value. That is what we are doing in the second figure, right? We are pointing heads to its next value, and we are deleting the first node of that linked list. So that's how we are performing the delete operation. And of course, its time complexity will be 1 because we are not what we can say, we are not considering, we are only deleting first, right? So we don't have to traverse through it. That was deleting from the first node, and if we want to delete from the last, then what we will do, or at a given position. So let us see through a diagram. Let us see, we have four nodes in our list, right? Head is pointing towards the zeroth index or the zeroth node, and we have four nodes on the list. Now, if we want to delete a node at what the second index, right? Let's say the node which is having value 30. Then how we can do that? So in that case, we have to keep two pointers with us for our help. Let us see how. We will keep a previous pointer and we will keep a current pointer. We will not do anything with the head because head is has its place. And what we are doing is, firstly, we will point our current to the first node and previous would be null. So by the name, it suggests that current would be the current node on which we are, and previous would be our previous of that current node, right? So we incremented our previous and current. So current is at index 1, previous is at index 0. Then we again incremented our current and previous. Current is at index 2 and previous is at index 1. Now, if we want to delete the node at second index, what we can do is we can set previous, which is uh, pointing at first index. We can set its previous next part, which is currently pointing towards second, to current's next part, right? So what we have is we have access to second node and also first node. So what we want to do is we will do something like previous next part, which was actually pointing to the second, we will point it to the third node. How we will do it? We will say something like previous next part is equals to current's next part, right? So this, in this case, this link is broken, and uh, we have our first node at index first pointing at the last one, and simply after that we can delete this current node because we have access to it. So we can, in Java, we can either make it null, or in C or C++, we can use a delete function for deleting that. So that's how it will work. And the algorithm is very simple. We will have current will be head and previous will be none at the starting. We will iterate and we will update current and previous. And after we have reached the position where current is pointing where we want to delete, in that case, what we'll do is these two operations. Previous next is equals to current's next. What that is doing is previous, which is the second one, sorry, the index first, its next part is current's next part. So we are skipping this second node and we are creating a link with third one. And then we can just simply delete the node. That's how it's going to work. And since we are iterating, the time complexity will be O of n in the worst case. Why? Because if it is at the last position, so then we have to iterate through the array first till the last, right? Okay, so just a minute, guys. I'll be back. Okay, that's our deletion part. And now we have seen traversal, so searching would not be an issue for you guys, I think, because searching is just traversing and seeing that if we have our key or not, right? So in search, what we have are we've got our key, and we'll simply run a while loop. That while head is not equals to none, we'll check that if head's data is key or not. If it is, we'll return true. and if it is not, we will just update head to point towards the next node, right? And if the loop is over and we haven't found the key, then we can return false. So again, same as in the array, the time complexity of the best case would be O of 1. When would be the best case? If the uh, the data or the key which we are searching is present at the first node itself, or the node at the 0th index. So that would be our best case. And the worst case would be if it is not present in the list, right? So we have traversed the list, we have done n operation, our time is proportional to n, and our time equation is linear in nature. So we can say that the worst case would be O of n. Right. So I think we can do that. Okay. So now comes a question which is very basic, but the programming community and the memes have made it a very big thing. That is reversing a linked list. If you follow some channels on Instagram or something, you might have seen memes of this question, right? That is reversing a linked list. It is a very easy question, but people have made it very difficult. So what we are doing in this one is, this is our basic list, right? The head is pointing to the first node, first is pointing second, second is pointing to third, and third is pointing nowhere, it's null. Now what we want to do is, we want our head to be at the last, and we want our first node to be pointing towards null or to be pointing nowhere, and we want to reverse all the links in our linked list. So that's what we want to do. Now the basic idea of doing that is, we will require 3 pointers. So let's say this was our list, head storing 10, 20, 30 values, and we will need we will need 3 pointers for iterating through the list and reversing the links. Let us see how it is performed. So we have our current, previous, and next pointers. So by the name you can at least have an idea of what is happening here. Current will be pointing towards the current on the node on which we are currently. Just a second, guys. Right, so current will be pointing towards our current node, previous will be pointing to the previous node of that current, right, as we saw in previous algorithms, and the next will be pointing to current's next part, but at the starting we have made both of them as null. Now we'll start the algorithm, and what we will do is, at the starting, what has happened is, we have set our current to the first node, previous is of course null, and our next is the next node of the list or the second node of the list. Now what is happening is, we have to reverse that link, we have to change that link to null, or to be specific, to our previous pointer. Now what we can do here is, we can set current's next part, which was pointing to next or the second node of the list, we can change it to null. So we have reversed this link, and we have done it for our first node. Why we are having these 3 variables, it might be clear for you to you all guys right now, because if we have made this link to null, then we definitely will be losing a contact with the next nodes of the list, right? Because here after the first node, we don't have any contact to the next node. So to keep iterating through the array, we need a next pointer as well, right? So similarly, what we'll do is, we'll update our next to the next node, we'll update our current, as well as we'll update our previous. So in the next thing, in the next the downward, you can see that our previous is now pointing to the first node, current is second, and the next is third. Now this first link was set. Yes, it was first node was pointing to null in the previous uh, diagram as well. Now we'll do the same thing. We will point currents next to again previous. So this node, this link is also changed, and we'll again update the previous current and next parts, and we will do the same thing again, right? What has happened is our next, now next is, let's say our current has to go to the last node, then where the next node will be, next node would be null because there is nothing after this node. So next would be null, and oh, I skipped one step here, I think. Yes, I skipped one step, so I'll explain in this slide only. The same thing is going to happen, and the next step would be, the next is pointing to null, our current is the last node, and our previous is the second node, which is storing the value 20. And again we will do the same thing. We will make our link of our current node to the previous one. So that's how we are reversing our links in our linked list, and we are iterating through it also. And after that, what will happen is, at the last we will again increment the previous and next pointers, and the at last previous would be pointing at the last node of the list, which was last when we started with the list, right? And at the last we can just point them to null because we have no use of them right now. And what we can do is, as our previous is now pointing to the last node, we can just say that our previous is equal to head. So the head is now pointing to the last node, the last is pointing to the second last, and similarly our whole list is reversed. So that's how this algorithm works. This might be a little bit confusing at start, so I would recommend to go through this PPT again to have a better understanding of it, right? Yeah, so this is its algorithm. So we have, as just we saw, we had 3 pointers, right? Previous, current, and the next node. So at the starting, previous and next is null, and our current is equals to head, which is the first node of the list. Then while our current will not reach null, as it did in this diagram, you can see, we will continue this loop, and what we will do, we will first set our next to currents next, so that we can have the address of second node or the next node. And this, the second line, which is current dot next equals to previous, this is what changes the links, right? Current dot next equals to previous, it means, like in let's say this diagram, where previous is at the first, current is 20. So current dot next equals to previous, what it does is, current dot next was pointing to the last node, which was having value 30, and current dot next equals to previous means now this link has shifted to previous. And similarly we will update the current, we are updating current to the next node. So the current is now reached the next node, and we will do this iteration till our current is null. Now at the last, what will happen is, our current would be, or sorry, our previous would be at pointing towards the last one. So in that case, what we can do is, we'll just do something like head would be equal to previous. So now head is, which was actually pointing to the first, is now pointing to the last node. So we have successfully reversed the linked list. We have reversed all the links, and that's it. Our algorithm is complete. Now, since we are iterating through this linked list once, so in that case, our complexity would be O of n, big O of n. Yeah, that was it, and we can see the differences now. So right, so we'll see the differences. uh, right, arrays versus linked list. Now array is a collection of elements of similar data type, right, that you have seen. In linked list what we have is a collection of objects, or which are also known as nodes, where node consists of two parts, that is data and the address of next or the next node, right. Array elements are stored in contiguous memory location, and linked list elements can be stored anywhere in the memory, or can be randomly stored, and this random storage will depend on your compiler. This, you don't have to decide this, that okay, this is our address, so we will make this next node address to something that is abstract to us, that our compiler will do, right. And the next point is array supports random access, right. We discussed about random access, that is we can randomly access any element of our array in just O of one time, that is in just one operation. And we saw how that operation is performed, that is the base address plus index into the size of the data type, right. But in the case of linked list, it is a sequential access, right. Why we are calling it sequential access? Because as the nodes are stored randomly in the memory, we we cannot have all the addresses together. We cannot find all the addresses in just one operation. And for that, we need to traverse through that list one by one to access any node in that list. So to access any node in this list, what we have to do is we have to sequentially traverse the list up to that element, or up to that node. And to access the nth element of the list, the time complexity is definitely going to be O of n, because we are doing traversal, right. So let us see some more points. In an array, insertion deletion operation takes more time, as the memory locations are consecutive and fixed. And in linked list, what we have is insertion deletion operations are fast in the list. Why is that so? Because we saw that the time complexity which we discussed was same in both the cases, right. It was O of n in array also, and O of n in linked list also, right. But why we are saying in linked list it is faster? Because in array what we are doing is we are having more operation. Why we are having more operations? Because we have to shift all the elements, like we saw the worst case of insertion, right. In that we have to insert at the 0th index, so we have to shift all the elements, and that is what takes more operations. That is what increases our time for insertion and deletion. And in the case of linked list, we just have to traverse, right. We just have to traverse. We have to reach either the previous node or the current or the node where we have to insert, and we have to just change the links, right. So in that case the operations are less, and in this array the operations are more. That's why we say that in array, insertion and deletion takes more time, right. The size of array must be specified at time of array declaration, that we already discussed. That size has to be previously pre-decided by you, right. And in the in the case of linked list, size is variable, because it is not something which is uh, having or storing nodes directly, or by default it is storing some nodes. It grows dynamically, and more nodes can be added to it as we wish, right. Now the next point is memory utilization is inefficient in the array. Like for example, the size of the array is 6, and it consists of of only 3 elements, then the rest of the space will be unused. Yeah, that is true, because like for example, if you have a question in which you have to use an array, and for example, in that case, the maximum length of the array is given is 100, that your test cases will use a maximum elements of 1000. So you have to, if you are using array, you have to previously decide, you have to pre-declare an array of 1000 elements. And if in a particular test case we are using only 10 or 15 elements, then the rest elements or the space allocated to the rest of the array is unused, right? Memory utilization is efficient in the case of linked list. Why? Because it is not using pre-allocated space. It is dynamically allocating space whenever we require it. And whenever we delete a list, a node in the list, we can deallocate or delete that memory during running our program, right? So that is what makes linked list more suitable for the cases when we have very large number of elements, like we have a million or some elements in those ranges, right? And the array can be single dimensional, two dimensional, and multi-dimensional. And we also have linked list that can be linear, or singly linked list, doubly, or circular linked list. So that's are the type of the linked list. So can we cover types also in this lecture? Can we do that? Because we are already ahead of time, as you guys
No,
wish.
sir, I don't think so. I mean, there is a time constraint as well.
So, okay, we'll continue here. Okay, so the type of linked list. The linked list we studied right now is singly linked list, right? Because as why it is called singly, because each node is storing the address or is pointing towards its next node, right? Like here, if you see the first node, which is having value 30, is pointing to the next, then next, then next, and then at last null. So this is what is singly linked list is. Now we also have doubly linked list. What doubly linked list is, what the structure we created when we were seeing how the list structure is created, we had a pointer to the next node. Now we can also include a pointer to the previous node itself, right? So in this case, we have a structure which is having data part, a pointer to the next node, and also a pointer to the previous node itself, right? So in this diagram, you can see that the first node, its next part is also pointing to the next node in the list, and its previous is pointing towards null. And similarly, that's what happens in all the nodes of the list. So in this type, our node has three parts. That is a next pointer, which is containing the address of next node, a previous pointer that is containing the address of previous node, and the data part, which is containing the data. Now we have two more variations in our linked list, that is circular and circular doubly. Now what that means, circular by circular, it might be clear to you and seeing the diagram also, that at in the case of singly linked list, the last node was pointing to null. Now we have changed it. Now we have changed it to the first node itself. So it is kind of in a circular fashion. Now some logics will change. We are inserting, or we are traversing through the list. Definitely they will change, but we will not see it here. We will provide those to you as well in the resources. And we also have doubly circular, that is the mix of circular and doubly linked list as well. So each node is having a next and a previous, and just the previous of the first node is at pointing at the last, and the next of the last node is pointing at the first. So that is your circular doubly linked list, right? Yeah, so that was it from my side. Now we can move on to question and answers.
Thank you, sir. The presentation and the PPT were both amazing. And guys, if you have any doubts, you can unmute yourself or you can type it in the chat box. Guys, if you have any doubts, you can unmute yourself or type it in the chat box. Now is the time.
How amazing it is, right? Everything is clear.
Sir, there were a few questions during the sessions. I just sent it in the chat box.
Okay. Can we see implement part of DSA? Yeah, that's what we did, right? We did it in pseudo codes, and you can implement it in any language you want. We will providing all those details in resources as well, because we couldn't extend this lecture to a 5, because if we showed you all the implementation, it would be of 5 or 6 hours, right? And the next question is, there are no pointers in Java, so how linked list is using there, and can we use bubble sort from middle of the array? Okay, so the first question is how linked list is used, as there are no pointers to Java, right? So Java has pointers and it doesn't have pointers. So there are, it is, we can say it works both ways. Why I'm saying that is, Java actually uses pointers internally, but it has not provided us uh, the access to them, right? So the pointers in Java is abstract from us, and that's what. And if you want, you can use pointers, but not exactly. We use them. We call them pointers. We call them references. So that we will see, that you will see in resources, that how in Java we can store the addresses of the next nodes as well. In Java, what we say is we use references. And the next question is, can we use bubble sort from middle of the array? If you use bubble sort from middle, then you are leaving the array, you are leaving all the elements which are in the left part. So you will not be traversing, so you cannot sort that array whole, the full array, because you have to access all the elements, and that's only how you will sort the elements, right? Right. So please explain again to be on this slide. I don't know, Nishant, what do you mean by to be?
Nishant, can you please specify the topic as well? You can just type it in the chat box, Nishant.
Okay, so I think Nishant left. Okay.
No problem. That's okay. So I guess, guys, if you have any more doubts, you can just ask right now.
Okay, there's something. Yeah, yes.
Yeah, we'll provide the recording, and we also have a YouTube channel. We'll provide all the links in the chat box. And we also have a Telegram channel. We'll be happy to clear your doubts there as well. Okay, so we'll just provide you the links in the chat box.
No more questions. So I've explained it very well, I think.
Yes, sir, definitely. The explanation was top notch.
Okay, if there are no questions, we can end then.
Yeah, just 2 minutes more. We will just provide the links and we can end. Guys, and please fill the feedback form. We are open to all the suggestions. Okay, please fill the feedback form. And if you want to see the recording or you missed any part, so you can always go to the YouTube channel. Okay, so that's it from my side. Thank you so much for joining, and you've been a patient audience. And thank you so much, sir, for sparing a beneficial time. I mean, the PPT and the presentation were both amazing. Thank you so much.
Yeah, thank you all for listening to me, and I learned a lot from you as well, and also from the participants. Right, so we can end here.
Yeah,
Okay,
we can
so
end. Okay.
for joining.
Thank you, guys. Have a nice day.